Well, let's finish this heavy symmetrical top. You remember we wrote the Lagrangian for the spinning top. So it's a rigid body with the axial symmetry, and it's fixed here where it touches and this is gravity, and it's spinning, okay, about the symmetrical axis. And I wrote the Lagrangian, so I call so I1 is equal to I2. These are the the moments of inertia with respect to the principal axis. So two are equals, and I call them A1. So the kinetic energy for this object in terms of the Euler's angle, I think this is the last thing we wrote last week. And then you have another, well, I guess I3, that is the third one, that is the only one that is not, so it's this one. These two are equal. And it's psi plus phi dot cosine theta square. And then minus the potential. Right. So I think. Okay. So after this is a Lagrangian, so you should study it as any other Lagrangian that we have studied. So the first question is, so we have 3 degree. I mean, we have the 3 Euler's angles that are our 3 degrees of freedom. And if you remember, what is the first question you should ask yourself? Even before, I mean, it's up to you, but either you write directly the Lagrange, the equations that you can, the Lagrange equations, but those are going to give you second order differential equations, right? So it may be a good idea to look first for first integrals, that is some conserved quantities, right? Because as I said, I think I bore you enough about this, but it's a useful thing to remember. Those are going to be first order differential equations, so in general are going to be simpler. So how do I look for conserved quantities? Well, is this nice things that if you have a cyclic generalized coordinate, the conjugate momentum is conserved, right? This Noether's theorem. So what is here? Do I have any cyclic variables? So look and tell me. Yeah. So time for sure. So the energy is conserved. Okay. Well, these are 3 angular. So which one? So psi, but also phi, right? There is no explicit phi. So you have not 1, but 2 angular momenta that are conserved. So just by looking at this thing, right? So you can say that these 2 coordinates, and then t, of course, the energy is conserved, but that in a way goes without saying. And therefore, I know that if I write the conjugate momentum, the momentum that is the partial derivative of your Lagrangian with respect to the generalized velocity, the dot of the psi, and also, because also phi, so also the dl d phi dot, these 2 quantities are going to be time independent. They are going to be conserved. So if I take the total derivative of this, it's going to vanish. So let's do that. Let's do that. And what is this thing here? So I have to take the dl psi. So you see psi dot is only here. So it's going to be I3, right? Psi dot plus phi dot cosine theta. Okay? So this is going to be a constant quantity in time. That means this combination is going to be time independent, so that if you take the total derivative of this with respect to time, this vanishes. So I can give a name to this, okay? Well, in general, you know that this is what? You remember how you go from the angular velocity to the Euler's angle. This is actually omega 3, right? You remember I wrote it here, how you go from. But because of this conserved quantity, because of Noether's theorem, this is just a constant. It becomes useful to, so that means this was a constant to start with, but this is constant, so I call it A. You see in a second why, sorry, I call this constant, I mean, I can call this anything I want, right? I can call it whatever, but I decided to call it a constant times I1, because you understand, in a second I'm going to collect this term. So how about this other? This other is a little more complicated, because you see that phi dot is here, but it's also there, so you're going to have two terms. So one is, it comes from here, so it's I1, so you see it's a square, and you have a phi there, so I get this 1 sine square theta that comes from there, but you also have a term here, right, with a cosine square, right? You have to expand this. So actually you have two terms, I3 cosine square theta multiplying phi dot. You see that? One from, so I'm looking at phi dot square, so one comes from here, then I square this, so the other one comes from here. So I have one proportional to I1 from the first term, one proportional to I3 from the second one, okay? But I also have the cross term, right? So I also have a term that goes like I3, the cross term, so psi dot cosine theta. And these two, by definition of the cyclic variable, has a momentum p phi that is constant. And again, I call it a constant that I write to be proportional to I1. Okay? So I have two equations, you see, of the first order. So I'm almost there, because then I have the third cyclic variable that, as your colleague pointed out, is time. So that means the energy, right, is conserved as well. And the energy is T plus V, so it's just these things with that sign switched off. So I guess I'll do it this way here. No? Yes, that's the nice thing about the blackboard. So I have three unknown functions, and I have three equations, so in principle I can solve the problem, right? So let's do it. Well, there are many ways to do this, so mine is just one possibility. So I have to massage these three equations. So let's first try to write what is phi dot, right? You see, I have this. So for instance, let me take from this one, from this equation here. So the equations are these. And they are on the top. So from this one, you see that I can write I3. So look here. I can write I3 phi psi dot. I take this part on the other side. So it's equal to I1 A minus whatever is left there. That is phi dot cosine theta. Okay? And so now I have this piece here that I can plug in here, and I get rid of the psi dot, so then you see I have an equation that is just phi dot equal to some function of the other variable, and in fact I have I1 phi dot, this term here, sine square theta, plus, well, I'm replacing this with these two terms, so you see that I have a term I1a cosine theta from the first one. And then you see that this one, when you plug it in, cancels that one. So I have all this is equal to this constant that I call I1b. So now I can extract phi dot is equal to whatever I have there. You see, now you see also why I put why I call these two constants, I factorize out the I sub 1 in these two constants, because now it comes handy because it drops out. So phi dot is simply b minus a cosine theta divided by sine square theta. So if I knew theta of t, I could integrate this and find phi of t. But of course, I don't know yet what is theta of t, because that is the solution of the problem. So I'm not there. But anyway, once I know phi dot, I can plug it back here, right? And if I plug it back there, you see that I get an equation for psi dot, right? So I take this, I put it in here, then I have I1a divided by I3 from the first term, minus this combination. So cosine of theta, I3 simplifies, cosine theta times this coefficient, b minus a cosine theta sine square theta. So 1 and 2. I have my two equations, the integration of which, if I integrate them, so now I only need to, you see, if now I take those two psi dot and phi dot and I'm plugging into the energy equation, then I will have an equation for theta dot, and then I'm almost done. So let me do that. So I only need this. This I don't need any longer. So 1, 2, and 3 is this one. So let me so plug in, and if you do that, since we are a little short of time, I just you write whatever it comes out constant. Remember omega 3. It was this thing here, right? If you can still read it. It was psi dot plus phi dot cosine theta, okay? So this is it was a constant, so this is a constant, the energy is a constant, omega 3 is a constant because of this Noether's theorem, and everything else, well, the first term, you keep it as it is, and the others, you see that when you plug in these two equations in here, you get something that is this. That is the third equation that you need to solve the problem. So you can take everything on the other side, and then you get theta dot. Okay, so in principle, this is these are the equations that if you solve, you get your trajectory, that is theta, psi, and phi as a function of t. But as I said, I don't really want to do I don't want to solve these equations. I just want to discuss qualitatively what the solutions of this problem look like. And you see that this looks like, you remember the one-dimensional effective potential, right? It's just a sort of, so this is like the velocity, right? And this is like a single variable that by varying gives you some shape, and then you can discuss the allowed motion. So in other words, what I say is that so these are constants, so you shouldn't worry too much. So let's just give them some names, okay? So what I'm saying is this part here looks to me like an effective potential of this variable theta, right? Because this is the actual potential, and here you have an extra term that depends on theta that is sort of you have to take into account if you want to discuss the motion, right? Remember, in the Kepler problem was that term proportional to the angular momentum, right? So this part is the effective potential, and this is like the kinetic energy, right? So let's give a name to this term. This is a constant that I call, let's make it simple. So I want to, so let's multiply everything by 2i, right? So that I can drop it here, and then I get it here. So then this constant, I call it alpha, okay? The first letter of the Greek alphabet. Then, so so I guess I should put this. So then this constant here, the coefficient of this, I call it beta, okay? And you remember that A and B, you remember, those are where, you remember what they were p psi divided by I. And this was p phi divided by I. Just that's, you already have that it was two blackboards ago. So I wrote all the things that are constant as some names. I gave names to all the constants. And then, you see, this equation is just, I write it up there. So if you allow me, I remove the energy condition because it's this in here. Now that I name this constant, this is just alpha equal theta dot square, right? This plus, well, I gave a name to this effective potential. So I have b minus a cosine theta square divided by sine square theta, this term here, plus just beta cosine of theta. So now this is the equation I want to discuss. And I erase this. So this is the equivalent. So this is the effective potential. This is the kinetic energy. This is just a constant. And you see now I can use this general idea that if I study the properties of the solutions of this equation, even without solving the equation, I can understand how the motion is taking place, right? And again, I can call u the cosine of theta this time. Instead of calling u 1 over r, like in the Kepler problem, here it comes natural to change variables. And then you see that this is a differential equation of the form u dot square equal 1 minus u square alpha minus beta u minus b minus au square. Okay, you can see this, or maybe not, depending on how your prowess, mathematical prowess, but anyway, I mean, you see, you have to change variables, then you will see that what you get is this. This is a nice form for the equation, because you see that now the solution is going to be what? You see, here you have a du dt square, right? So the solution of this is going to be an integral, right? You take this on the other side, then this comes downstairs with a square root. I'm going too fast. Yeah, right. So, but that stopped me. Where you lost contact. up to here, up to here is clear. Okay, that's very good. So just one line. Okay, so I change variables from theta to u. Then if you change this, you have a derivative here, right? So just do this. You see that u, so there you have to compute instead of d, so this is d theta dt square. So you have to change to u. You will see that you get some extra cosines that simplifies, and then you get this. Okay? If you don't believe me, then you do it at home tonight and you verify. So these two are the same equations, only with this other variable. Now, we are almost there, right? We have those, I just changed this equation. So this is du dt square. That means that this is like a dt, right? You take dt there and this on the other side. So you have dt du, the square root of this. 1 minus u square, alpha minus bu minus bau square. Right? So you see that the solution is just t equal the integral from u at time equal to 0, u to the time t, right? If you do this integral, then you invert whatever solution you have u dt. If you have u dt, you have theta dt. And if you have theta of t, then you plug in here you integrate and you get side of t and 5 of t. So you have solved the problem. So that for sure you can do. But again here, this is a rather complicated integral. And it's again an elliptic integral. Surprise. They keep on popping up. And it's cubic in u, right? You see. The highest power is this u cube. So in general, okay, you can find, depending on the value of alpha, beta, b, and a, which depend in terms to the initial conditions, you can find the solutions of this integral, okay? But really, we don't need to do that, right? Because, as I said, just by looking at the property of these solutions are linked to the roots of this polynomial, right? Because depending whether these roots are, you are going to have real solutions or imaginary solutions, right? Like before, because you see, the problem is that your motion, the velocity, like for the Kepler's problem, must always satisfy the fact that it's a positive real quantity, right? So according to where you are about these roots, this may become imaginary, then that is not an allowed region of space, right? You remember what we did for the, let me do the drawing. Actually, one can also observe that, remember I told you that if you take this system and you remove gravity, that is called a gyroscope. It's a simpler problem because that corresponds to taking beta equal to 0, right? So you see that if beta is equal to 0, this is not a cubic equation. It's not a cubic polynomial under the square root. It's only a quadratic one. And if you go back to that famous book with all the integrals, you will find that if this is quadratic, you always have the solution. You don't have to go to the elliptic integrals, okay? So it can be solved, and it's a much simpler problem, okay? So that was the gyroscope. But let's stick to this one, in which this, in fact, is different from 0, and therefore this is a cubic, so it's a little more so you can call, so let me call this cubic function, I call it f of u. And as I did for the Kepler problem, I draw this function. So here you have u, and here you have f of u. And you understand that the roots of this polynomial are the turning points of the motion, right? Because you see the root is where the velocity goes to 0. Okay, so that means the velocity goes to 0, so it's changing direction. So it's where the motion is changing. Okay? And remember that theta is this angle here. So the roots of that is where, you remember what I said last time, the motion is going, so it's spinning, then it's moving like this about, okay, this precession. And here we are looking at the theta. The theta is this motion here, is this motion of nutation. Okay, so it's moving like this, but it's also moving like that. And the roots of this polynomial is where the velocity changes sign. So it's moving like this. It's telling you when it stops moving like this and it comes back. Okay, so it's describing this part of the motion. The rest of the motion is sort of trivial because, as I said, it's just spinning and moving with this velocity, is moving about the vertical directions. Okay, so this is the precession. Okay. Okay, so bear with me. So how is this function? How can you draw this function? First of all, how does it go? So I want to do a back of the envelope analysis of this problem. So I just want the shape. I don't want the actual values of these roots. I just want the general shape of this curve. And you see that for large values of u, of beta, it goes, I mean, if this is large enough, okay, it goes like beta u cube, right? So what does it mean? It goes like u cube. So for positive value of u, it goes like this. And for negative values of u, it goes like this, right? It's like a cubic curve. So then there are three roots. So it must be doing something like this if you connect these two. Meaning that it has one root here, and one root here. So then you see that depending where you are, what's so funny? Depending on where you are, you can describe the motion. For instance, let me see if I can get it right. So you see that here is negative, okay, and here is positive, as we said. So this function, to have an actual solution, you need this quantity to be positive. So the motion has to take place here, between these two roots, okay? Actually, it cannot be up here, right? Because remember that u is the cosine of theta, so it cannot be, the cosine has to be, so essentially, I don't know, 1 is somewhere here, so it has to stay there. So it moves between these two roots. And you see that the theta is the arc cosine of u, right? I guess. So if I draw the motion, so I draw a sphere described by the axis of the so this is the vertical direction, and then you have the axis of your top that is spinning. As I said, if you don't have notation, then that axis will just move along a curve like this. Do you see this? So this is a sphere on which I'm drawing the motion of the axis of my top. So if there is no nutation, meaning that the angle theta is fixed, then it's just moving like this, just with a precession like that. But this is not the case, or better, if these two roots are the same, if the coefficients of this polynomial are such that the two roots are the same, then you are exactly in this situation, that you have a spinning top and it's just precessing. But in general, you see, you have a range for which this function is positive, so that you can have a velocity well defined. And so in that case, you have a range where this is, I guess, is theta 2 that correspond to that root u2, and here you have theta 1 that correspond to the other root, and your axis is moving like this, is nutating back and forth, because the motion has to be between these two roots. So this motion is called nutation. Okay, and you see that theta dot is the velocity in going back and forth, and you see that when he reaches here, theta dot becomes 0 before changing sign and coming back, changing sign, coming back, and so on and so forth. Okay, so it's described by this. By this. Actually, it's even more interesting, but I'm not sure we want to dwell on this, because you see that it's not only a problem of theta naught. The motion here is described by phi, and phi is this, right? And you see there is an interesting match here. Okay, I'll just say it in words, that you see, you come up here with a certain velocity in the theta direction, and then is the question, what is the velocity at the same time in the phi direction? So what is the sign of phi dot that is given by this equation when you reach the point there? You see, it can happen that they have the same sign, okay? So it could be that phi dot has the same sign, I don't know, it depends on the relative values of this coefficient with respect to those, than theta dot, okay? Or could be that it has the opposite sign. And you understand that if they have the same sign, this is the situation, because when this comes here, it has the same sign as this component here, so it goes like this. But if it has the opposite sign, then, okay, it's difficult to draw it. It goes like this. Well, it goes like this. Because it comes up with that sign, but here it's moving slower, so it goes like this. And if they happen to be exactly 0 at the same time, then you have a trajectory that I guess is like this. So exactly, it comes back. So that's a nice so it would be nice to spend more time on this. Well, I don't know if you agree, but okay, it's an interesting system, and this is the solution. Then, okay, this is the general solution. Then, if you give me the actual values for these constants, then you can solve this, plug it in there, then you find these trajectories exactly, and you will see that they move like that. So what is happening? You start out, for instance, here, because of the, so this is spinning, but because of gravity, the top starts falling. Right? It starts falling. But because it's spinning, there is a torque that brings it up. So actually, it's going up. And then it's falling again, and then it's brought up. And depending on the relative signs of these two motions, it may go like this, or it may go back like this, or it may even be sharp like that one. And if you look carefully, I mean, this is not easy to see the difference between these three cases on a small top. But if you look carefully, you will see that depending on the top and the initial conditions, you may have these three classes of solutions. Okay? Questions? So as I said, this is a system that has been studied very much, like Sommerfeld, who was a German physicist who was the Heisenberg's teacher, wrote an entire book just on this, just explaining this in what I just said, and many more in more details. So, okay. What else can one say? So if you don't have questions, I move to the next chapter. Questions? You need some time to digest it, or? Okay, I mean, I had to summarize, but I think you have the information, enough information to go back to your textbook and understand. I follow very much what Goldstein is saying. You will recognize the same picture. So I think if you read it, you should be able now to read it and understand it. You were about to say? This? What? The three cases, or just this? The three cases, or just the difference between these two? It's just a different. You see, you have to look. So phi dot is the velocity in this direction, right? And theta dot is the velocity in this direction. So you see, depending on the relative sign of these two velocities, you can have, if this comes up, why this goes like this, right? This is coming up and this is going like, then you have this, right? But when you are coming up, you have the opposite sign of phi, then you go like this. You go a little bit back and then like this. If you happen to have theta dot equal to 0, that is up here, exactly also phi dot equal to 0 in that instant, then it goes like this. Because it's like it stopped for a second and then it keeps on moving. It's the composition of two motions, right? I don't know if it's clear. You should, it's like, we need a sphere here. A sphere with this axis, and this axis is moving like this, but it's also moving like this. So you compose two motions, and the composition of these two motions can be either like this, as I draw it here, or like this, that it goes like backward for a little bit, and then, this is amazing. It's an amazing motion. You really see it. So this thing is going like this. It's like drunk. And this, like this. And this velocity, it depends on this coefficient and the initial condition, therefore. So depending on the specific solution, you can end up in this situation, or that situation, right? Exactly like the orbits, depending on the initial conditions, you could have a closed orbit that I guess correspond to this, and the open orbits, like the comet, and so on and so forth. All right. So this was an application of to the motion of a rigid body, and now we are ready to the next chapter. As I said, that is the Hamiltonian approach to classical mechanics. So that, I guess, is also the last subject we are going to discuss. So even in these final examples, what I wrote were Lagrangian equations, even though I didn't write the Lagrangian equation, but just the first integral. Now, if you remember the list of subjects I wrote down the first day, next in that list was this Hamilton equations of motion. So what is that? So, yeah, what is that? So we had Newton's equations, then we wrote Lagrange equations, and people, kept on thinking, and they decided that that was not enough, and we needed an even more powerful technique. I mean, the physical meaning is always F equal ma. But as I hope by now you should appreciate it, that by making things a little more complicated, like in the Lagrangian, actually you acquired a more powerful tool, okay? And so this is the next step, an even more powerful tool, as you probably already know, because this Hamiltonian, did I write that right? Yeah. The Hamiltonian, you already met these things in quantum mechanics, right? Am I right? So you may wonder where that comes from. Why do you need that? And it comes from here, from this description. So what is this? Why is this any different? Okay, let me. And also in statistical physics, have you done thermodynamics? You haven't. In statistical physics too, you use the Hamiltonian, right? When you try to describe thermodynamical quantities as averages over the motion of many particles, usually you use this language. Anyway, you use it everywhere because it's the natural one. So let me remind you that the Lagrangian equations, so we start from the Lagrange equation, where these things that you had a number of generalized coordinates, and you wrote those equations like that. So if you have n generalized coordinates, you end up with n second-order differential equations that I just wrote. These are second-order differential equations. So you have n second-order differential equations. And to specify the solutions, you need 2n, so twice as many initial conditions, right? You need 2n initial conditions, because you have to specify the qi, the generalized coordinates, and the velocities at time t equal to 0. Or in some problems, you specify coordinates at 2 different points, depending. Okay, it's the same. You can either give 2n initial conditions or n boundary conditions. That depends on the problem. But let's just stick to this test. Now, this space here, okay, this space here is called configuration space. I already mentioned that. That is the space given by your coordinates. And you remember, you see, it's an n-dimensional space where your system becomes just a point. That's a nice thing to think about it, right? No matter how complicated the system, it is described by a point in this n-dimensional configuration space, right? So if it's actually a point, then it's a point in 3 dimensions. So the configuration space in that case coincides with space. But if it's like a more complicated rigid body with some moving parts, then it's a point, but in a larger space with as many dimensions as generalized coordinates. Now, I don't know if you have thought about this, but otherwise you think about this now. You see that here the velocities are sort of derived concepts. They are not primitive variables. It's not really independent. I give you the coordinate, and then you have you take the velocity of that coordinate, and you compute the velocity, right? So the velocity comes as an auxiliary coordinate. But if you go back to what we have just said, for instance, for the top, you see that the natural variables for the problems are not so much the velocity as the momenta, because you remember it is the momenta that are conserved if the coordinate is cyclic. So the natural conjugate variables to the coordinates is not the velocity, but rather the momenta that are always defined as this derivative of the Lagrangian, and that's why I call them the conjugate momenta. So from this point of view, rather than using q dot I, it's much nicer to use as variables qi and pi. So these are called canonical variables. Okay. Now, canonical, you know what that means? Canonical, I don't know, actually. It's you know, the canon is an established set of rules. So they were so impressed by all this that they called these canonical variables. And very often the Hamiltonian equations are called the canonical equations, right? Because that's it was considered very fundamental. So you see, what I'm saying, I guess, is that I want to move from writing my mechanical system by using qi and the velocities to using qi and the momenta. Okay, so it's a sort of change of variables. So how do you do a change of variables on some function in general? I don't know if you have seen that. Yes, sorry. Where? This? QI. It's Q. Yes, sorry. Thank you. So how do you do that? This is called the Lechon Transformation. Have you, another French guy, have you heard about Legendre transformation? You did. Yeah, Legendre. Thermodynamics, exactly. Have you all? You remember thermodynamics is famous because there are many functions and they depend on many variables, right? And it's very confusing. And for instance, I have here an example of these confusing things. For instance, there is a thing that's called enthalpy. You remember? And people call it H just to add, because we are going to call H the Hamiltonian. But okay, here this is thermodynamics. So. And you remember that enthalpy depends on S, that is the entropy, and the pressure, right? And then the next day they tell you that there is what a thing is called free energy, that is G. And G depends on the temperature and the pressure. So I use this as an example because here the same. You see, I start with L, that is Q and Q dot, and I want to end up on H, that is, so I guess, it is Q and P. So it's the same problem. I have a function that it depends on some variables, and I want to go to another function that is obviously related to that one, that is a function of a new set of variables. So consider this case here, I guess. I took this. So how do you go from one to the other? You remember that the equation for the enthalpy is that the partial derivative of the enthalpy with respect to the entropy is equal to the temperature. And the partial derivative of the enthalpy with respect to the pressure, so it depends on S and P, so you can take these two partial derivatives, is equal to the volume. I mean, thermodynamics is nice, I think. And it has been developed in a very formal manner, like this. And also consider that no matter what happens, thermodynamics will always be true. That's a nice thing, because it's macroscopic, right? You don't say anything about it. It'll always be true. Quantum mechanics may be wrong. The speed of light may not be right. I know, you can, whatever people want to tell you, but always you will have this, and always will be true that you cannot, the energy is conserved, and so on and so forth. That's the nice things about macroscopic physics. Of course, there are constants that you have to put by hand, right? Like Boltzmann constant. And there is where you hide the macroscopical things. So if you study macroscopic physics, you understand many more things, of course, than this. But you may be wrong. The next day somebody discover something, and that can be wrong. But this is very formal. It's just property of macroscopical stuff, and it will always be true. It's one of the things that we are sure about. Yes, I don't know. You never be sure, but certainly you're more sure about this than. So how do I transform? So first I want to find how I go from this to this and what changes in my equations. To do this, you do this Lechon transformation that is defined to be, you take the new function, is the old function, minus the product of the, you see here essentially you want to switch the entropy with the temperature. So you take the product of the functions that you want to switch. And if you take the full differential of this, right, is dh, but what is dh? You can write what is dh, right, because it's minus s dt. No, sorry, yeah. So minus dt, then you have plus t ds plus v dp minus t ds, right? dt t ds. Right? Do you see that? Because this, because of the equation, this is dh. No, sorry. This is just this. This is t. This is dh ds, right? And this is dh dp. And these two are just this. I use this equation. You have to use the equations that, but then you see that these two terms drop out, right? So, and then whatever is here, this must be dg dt, right? And this one must be dg of dp. So I get the new equation that are dg dt, this is a t, is equal to minus s, and dg dp must be equal to the volume. So through this Lechon transformation, you recover all these sets of equations that maybe if you didn't know about the Lechon transformation, you had to study by heart when you do thermodynamics. Okay, I mean, it's not important. It's just an example of the... So let me do the same here. Like I went from the enthalpy to the free energy, I want to go from the Lagrangian to the Hamiltonian. So I do the same trick. I have to introduce the new function. You see, the new function now is h. So the new function is the old function. Is the so I guess I decided to write it like this. So I want to switch q dot with p for each of the coordinates. So minus L. So maybe I should write it like this. So this is my Lechon transformation for the case of, so let's forget about thermodynamics. Okay. So by doing this, I'm going to discover the equations that are satisfied by H, that are going to be my Hamilton equations. So let's do that. So, well, I have to compare, like before, I have to compare dl with dh, right? And then I use it in here. So what is dh? I use this for dh. You see, I have pi dqi dot plus q dot I dpi minus dl. This is dh from this definition. What is dl? This we wrote it several times, right? Is dl dqi. What time is it? dqi plus dl dq dot I dq dot I plus dl dt, if there is an explicit dependence, right? But what is dl dqi? dl dqi, you remember, you see dl dqi is nothing but, this is p, so it's p dot Newton's equation. And what is dl dqi? Well, this we wrote it. It's just the momentum. So this is pi dq dot I. And what is dl dt? Is dl dt. So now I can take this and plug it in here. So you see I have minus p dot I dqi minus pi dq dot I minus dl dt dt. So as before, for the enthalpy and the free energy, I have that you see this term. Where is it? So this one cancels exactly that. And this, by definition, must be the total differential of H. So by definition, this coefficient is dH dq dot dpi. This is dH dqi, and this is dH dt, right? That's just the definition of the differential. So you see I have here my equations. This new function that I introduced, that is called the Hamiltonian, satisfies those equations there. So I write them here. dH dpi is equal to what? To q dot I, right? Then dH, the second one, qi is equal minus p dot I. And finally, dH, let's write it here, dH dt is equal to minus, see the dl dt. So these are the Hamilton equations, or the canonical equations, and you see that there are 2n plus 1. There are n plus 1, 2n plus 1, first order differential equations, right? In the two canonical, well, in the 2n canonical variables qi, pi. So this is a new way to try and solve a mechanical problem. Instead of writing the Lagrangian, you write the Hamiltonian. Then once you have the Hamiltonian, that is a function of qi, pi, you take this partial derivative, you get a set of 2n plus 1 equations, and you solve those. Okay? So how do you write the Hamiltonian? Well, one way is just to go through this definition, but often is not the fastest way. So usually one goes through the Lagrangian. You first write the Lagrangian and then you derive the Hamiltonian. Or if it happens that the energy is conserved, okay, then you can prove that the Hamiltonian is in fact T plus V. That is, it coincides with the energy. So in most of the systems that we are going to discuss, actually it's easy to write the Lagrangian because it's just the energy written in terms of the generalized coordinates and generalized momenta. Okay, so let's write some examples of Hamiltonians, unless there are any questions? Let's write some simple systems that so you get the feeling for this new object that we call the Hamiltonian. So, for instance, what is the Hamiltonian? I guess for a free particle, point particle of mass m. As I said, usually the simplest way to write the Hamiltonian is to write the Lagrangian, and then you change variables, because you write the Lagrangians in terms of the generalized velocities, and then you switch to the momenta. For instance, T is equal 1/2 mv squared. Okay, that's we like and love. The kinetic, well, this is the Lagrangian of a free point mass particle. Okay. So what is the, if you wish, in Cartesian coordinates, is this thing here. So how do I write the Lagrangian? Okay, the Lagrangian is going to be the same function, because after all, this is the energy, and the energy is conserved, but you have to replace the velocities with the momenta, right? So you first have to compute the momenta. So here we are Cartesian coordinates. So px is dt dx dot, right? So it's just mx. That is nice because it coincides with our understanding of what the momentum is. And then you see, from these equations, you can write x dot, that is the velocity, in terms of px, py, and pz. Therefore, the Hamiltonian for this simple system is just this. So that's the first Hamiltonian that probably you have met in quantum mechanics, right? Because that's the Hamiltonian for a free particle, right, moving in space. And what about if I write this in spherical coordinates? How about spherical coordinates? That too is something that you must have done in quantum mechanics, because when you describe the kinetic part of the Hamiltonian for the electron in the Bohr atoms, you have to write this in spherical coordinates. So how do you do that? Well, the kinetic energy in spherical coordinate, remember, is this r square sine square theta phi dot square plus r square theta dot square, right? So now you have to compute PR, P theta, and P phi. Then switch back to the Hamiltonian. So what is PR? PR, well, you read it off from there, is mr dot. And P theta, well, that is the famous angular momentum, right? So it's just mr square theta dot. And phi, p phi, is related to that, so it has an extra sine square theta phi dot. So if you now solve this r, theta, and phi dot in terms of the p's, you get that the Hamiltonian is now 1 over 2m pr square plus p theta square divided by r plus p phi square r square sine square theta. And if you add the potential of a central force, you have the Hamiltonian for the motion in the central force. For instance, Bohr hydrogen atom, or the motion of the Earth about the Sun. So what's so exciting about the Hamiltonian? Well, for instance, what happened if you remember that one nice thing about the Lagrangian was that sometimes you had the cyclic variable, right? Because then you had the... So what happened if you have a cyclic variable in the Hamiltonian? Think back at the... so I guess I should write back the... You see the... right. Yes. Yeah. Also, yes. So let's do it. You see the equations were q dot I dh dpi, right? Minus p dot I equal dh dqi. Let's forget about also the one with the time, but let's assume that the Lagrangian does not depend on time, energy is conserved, so h does not depend on time. You see that if you have a cyclic variable, that now implies, because by definition this gives you 0, right, for a cyclic variable. So again, that means that so what I'm saying, if you have a cyclic variable, you have exactly the same thing that you had for the Lagrangian. So everything we said about symmetries, property of symmetries, and the consequence of having a symmetry that translates in this language in a conserved quantity, it's all true. So what was nice for the Lagrangian is also nice for the Hamiltonian. Okay, so we didn't do that just for the Lagrangian. You can repeat all the steps, all the discussion that we have done about conservation laws also here for the Hamiltonian. But in a way, it's even more powerful here, because you see that if this is true, that means that this is a constant, right? Because the dot is 0. But now this p is not just a constant that comes about, as it was in the Lagrangian, right? It's one of the coordinates. So if you have a cyclic coordinate, in a way, also the conjugate momentum is just a constant, so it drops out from the problem. So you get a sort of double benefit in this case, because if you start with an Hamiltonian, oops. Okay. If you start with what I'm saying, that you see, you start with the Hamiltonian, and it's a function, say, of Q1, Qn minus 1, and not Qn, because Qn happens to be cyclic. Then you also have that you have P1, Pn minus 1, and then instead of having Pn, you just have a constant that I call alpha. So the benefit is twice as nice as in the Lagrangian, because not only you have you see, your Lagrangian did not depend on the cyclic variables, and then you could deduce a conserved quantity. But here the conserved quantity, the quantity that is conserved, was one of the variables. And that becomes a constant, so you don't have to integrate anything to find the value. It's just a constant. Whatever the initial value of that constant, it just remains constant, okay? So that's one of the reasons why the Hamiltonian was introduced, and you will see very shortly that this is the key of how you solve problems when you have the Hamiltonian that we are going to do very shortly, but I think next time. First, I want to discuss some more example of Hamiltonians. But just keep in mind this, that the way we will solve these equations is not by simply solve the equations, but we will look for transformations such that they become trivial, and then we will solve them. And this is the reason why we introduced the Hamiltonian. So that we are going to do on Wednesday, but before, so I want to discuss a few examples. So let's, meaning I want to write these equations for some problems that we have already solved, so that you gain some confidence with this formalism. So for instance, I wrote here, you remember the Hamiltonian in spherical coordinates, but a special case is the motion in the central force, right? And you remember this was actually a two-dimensional problem because of the conservation of the angular momentum, right? So the Lagrangian, you remember, so let's take a point particle, a polar coordinates, very simple, with some potential that just depends only on R. Okay, so I want to write, first I want to write the Hamiltonian. Okay, we already did there, but let's do it the other way. And then I want to write the Hamilton equations, okay? So what is so to write the Hamiltonian, this time instead of writing the energy, as I did before, I do it by using the Lechon transformation, okay? Just to show you that it's just the same. So first I need PR and P phi, but this we already computed. It's just dl dr dot, so it's mr dot. And dl d phi dot is just mr square phi dot. So from this I get that r dot must be pr divided by m. And from here I get that phi dot must be p phi divided by mr squared. This is the, p phi is just what we call the angular momentum up to now. So if I now write the Hamiltonian, remember the Hamiltonian, by using the Lechon transformation, I have to take the product of the variables that I'm switching, so PR r dot plus p phi phi dot, and subtract the Lagrangian. So this is the definition of the Lechon transformation now. So, and if I do this, you see I have everything in here, right? You replace r dot with this, you get PR square divided by m plus p phi square divided by mr square. Then you have to subtract the Lagrangian, but you have to write the Lagrangian in terms of r phi, and not the dots, but PR, p phi. And so you see that by using the same substitution here, you have minus PR square to m minus p phi square to m, right, plus VR. Therefore, the Hamiltonian is just, well, 1 minus 1/2. That's 1/2. That is nice because, you see, this is exactly the same result that we had by writing the energy, because I said if the energy is conserved, the Hamiltonian is equal to the energy, and this is, you see, is exactly the energy. This is the kinetic energy. Remember what we wrote, plus the potential. So that's the two definitions, as it should be, they are good. How about the equations now? Well, now I have the Hamiltonian. This is the Hamiltonian for a particle in a central force. And I know that so the equations, the Hamilton equation are P dot R equal minus dHr, right? And P dot phi is equal minus dH d phi, right? How about the other two? The other two are just this, right? The other two equations are the dH dPr, so dH dPr equal to R dot, dH dP phi equal phi dot. But you see that if I take this, I'm just go back to this. That is the original transformation. Ah? Ah, yes, okay. Thank you. Ah? What? 2m square. But also here. Well, there is a conservation of number mistakes. And so these two, so you have 4 equations because you have 2 degrees of freedom. These two are nothing but these two. So we already, and these two are what? Well, this, is there any dependence on phi here? No. So this is just a cyclic variable, and that is telling you exactly what I said, that h does not depend on phi. Phi is a cyclic variable. Moreover, this p phi is conserved because it's the angular momentum. So here, this is just a constant. You can replace that with L squared as a constant. And the only dynamical equation is then this one here. So I write it. That tells you that P dot R is equal to, so minus dH dr. So where you see you have a term here. So you have P phi squared, that is a constant, divided by mr cube with a minus, so this becomes plus, minus dVr dr. But this is the equation that we discussed many times. This is the effective potential, right, sort of, or better, this is the effective force, because now we have the P acting on the particle in the radial direction. So here you recover, so this is a P dot, this is an acceleration. So this is just Newton's law. Do you recognize it? I hope so. How about the pendulum? How do you write the Hamiltonian for the pendulum? Well, just the same as this. Let's write the Lagrangian. So we have a pendulum. So the Lagrangian is, well, many ways to write it. So for some reason I wrote it like this. right? See, this is just v square, right? V square for a pendulum, right? V is just L theta dot, right? So this is the kinetic term. And here's the potential where I put the 0 when the pendulum is at the lowest point. So this is a system with just 1 degree of freedom. So I only have one momentum, the p theta, that again is just dl d theta dot. So what is it? Just this, ml squared theta dot. So you see now, if I let's write the energy for this. Is just you just change the sign here. So all you need to write the Hamiltonian is to take this to substitute p theta for t theta dot. So you get 1/2 p theta dot square ml square plus mgl 1 minus cos theta. So this is the Hamiltonian for your pendulum of length L. And what are the equations of motion? Well, one is this one here. Remember, this is always theta dot is equal dh dp theta. That is just p theta divided by ml squared. So this is just sort of the link between the old and new variables, and the new equation has to do with p dot theta, that is minus dh d theta. So what is this? Well, you see from here that is just, so you have to take the derivative of this. There is a minus, but there is a minus there. But you get a minus there, so 3 minus makes 1 minus mgl sine of theta. And you see this is exactly equivalent to the Lagrangian equation that was gl sine theta equal to 0, right? If you plug back this, you get exactly the old equation for the pendulum, for the harmonical oscillator. But here you have to solve for p and theta separately. You consider them two independent variables. Actually, then I stop. You can draw the trajectories, right, in this. So the space of the canonical variables is called the phase space. Have you heard about that? Phase space. That is the space where you have your coordinates and your momenta. This is the most natural space to discuss classical mechanics. So it's a 2 times n dimensional space now, if you have n degrees of freedom. For instance, here you have 1 degree of freedom, so the phase space of the pendulum is a 2-dimensional space, so it's nice. It can be drawn on the blackboard, and how it is made is like something like that, right? If you have theta and p, the momentum on the other axis, you see that you can draw all your trajectories by using the energy here, right? So the trajectories are such that this combination is a constant, is the energy, and you can check that they are, you see, depending on the energy. So again, I don't want to solve the equations, but you remember that the motion was such, okay, clearly if the if the energy is between this value mgl and minus mgl, right? Then the motion of the pendulum, right? It could be either a circle in the phase space, like this, or it could be like this. So you can draw your trajectories that are your solutions in this phase. Okay, here's a simple example because it's a one-dimensional example. Then you can actually draw them. And even without solving the problem, you by looking at this equation, you know how this equation is a curve in 2 dimensions. And depending on whether this, so you call this the energy, depending on the size of this constant with respect to this, either you have circles like this, or you can have a more complicated curve in which theta keeps on increasing. Right? I mean, that is the case in which you give a lot of energy, then the pendulum goes like this, right? So theta keep on increasing, picking up 360 degrees. The other one is the one in which is oscillating like this. So the theta, you see, theta remains between the 2 values of the initial values. So, okay. Okay, I stop here. And next time, so on Wednesday, we'll start studying how to solve systematically Hamilton equations. Okay, there is a trick, if you want, a way of solving them in a systematic manner that make it the solution very, very nice.